Hi everyone, welcome back to another Calculus 12 video. We are doing 10.1 today, which is the area under a curve. I know that we've jumped from 9.1, but as I told you before, I've created a unit from a mixture of chapters 9, 10, and 11. And you'll see they flow quite nicely together, so it'll make sense. And let's dive right into our first example. So if you take a look at this, it says find the area under the curve y equals x squared from x equals 0 to x equals 4. Okay, so this is sort of revisiting old concepts, but it's looking at it from a new perspective as usual. And I've purposely chosen y equals x squared because I know that you're quite familiar with parabolas. So I'm going to quickly sketch this out. I know that you probably have a mental picture of what it looks like, but I think to actually visually see it is also helpful. And then notice how here it says we are interested in what it looks like from x equals 0. So basically from this point to a point where x equals 4. So I'm just going to mark 4 down there. It could be anywhere, but we're just going to assume that it's at that point. And then if it says find the area underneath that, I can kind of just scribble this in or color it in so you can get a sense of what it looks like. But we're basically interested in the area that's in blue here. And so when we are looking for the area underneath a curve, we would actually use the stuff that we learned last day, which is, remember this beautiful symbol, x equals 0 up to x equals 4. So we're looking for the integral, we would call this, or we're going to use anti-differentiation, the stuff that we went through last day, in order to do this. And we would use our equation here, x squared dx. So that would be like the derivative. And that's what we're actually using to solve or to help figure out what this would be. So we're working backwards. So to take a look at this and to work backwards or find the antiderivative of this, a reminder from last day, we would look at the exponent and we would add 1. So I know it would be x cubed, but I also know that I put the reciprocal of that 3 in front of here as a coefficient. So it'd be 1/3 x cubed, or another way I could say it is just x cubed over 3. It means the same thing. And then I'm also going to show you this notation here. We're looking for this from 0 to 4. So we can use that notation to talk about what we would call the lower limit and the upper limit. So, for example, can I color code this? I'm going to say that would be our upper limit because that's the maximum that it's going up to. And I would say this here would be the lower limit. So we're going to use this in our calculations. I'll show you how we would do this. So again, just to sort of repeat this, first step is we take the antiderivative of the equation that we're working with. Second step is we're going to plug this in to look for the upper limit and the lower limit. So I would take this and plug in the 4. So I'd get 4 cubed over 3. So that's going to, oh, you know what? Let me color code this. If that's our upper limit, I'm going to do 4 cubed over 3. And we are going to subtract from that what our lower limit was. Our lower limit is where we have 0. So it'd be 0 cubed over 3. Clearly, I don't even need to finish that or work on that because we can see that the 0 is just going to wipe everything out. So I would end up getting 64 over 3 because I really only need to worry about this part here since the rest of it just cancels out. That's how we do this. So if you have a question like this where you are looking for the area under the curve, you don't necessarily need the sketch. I just did that so you would get a visual representation to go along with the algebra and the work that we're going through. But we would take the antiderivative, we'd find the upper limit, subtract the lower limit, and that ends up giving us our end result of 64 over 3. You could leave it like that, you could change it to a mixed number, you could change it to a decimal, doesn't matter, but that's basically the idea behind it. So knowing that, let's do another quick one just to practice this. What I would suggest at home is that you hit pause and try this one on your own, since it's quite similar. And if not, just follow along. We're going to go through it together. And again, you don't have to do this, but we have past knowledge. We know that this y equals x cubed is a cubic function that looks somewhat like this. And this time we are looking for the limit from, oh my goodness, on the fly, I am going to change this. Let's change this. Let's do -2 just to spice things up a little bit, to get a bit of variety. And let's do all the way up to +2 so that we get a little bit of variety in here. So if that is what we are looking for, well, let's go through this. If that's what we're looking for, if we're saying from -2 up to +2, okay, let me just mark this on here. I'm going to say that's -2, and I'm going to say that's 2. Like, I don't know if I'm drawing this accurately, but I just want you to get this general sense of what we're doing. And if that's all the way up to 2, I would color in that portion as well. So you get an idea of what's going on here. We're looking for, oh God, I've made a big mess out of it, but you get an idea, you get the general sense of what it is that we're working with. Again, you don't actually need the diagram. We are just doing this to be able to get a mental picture of what it is that we're working with. I feel like that's helpful in the whole understanding of what's going on. And like I always tell you, I feel like that was missing when I was in school. That's why I'm doing that for you. So if we are looking for the area, let's go through again our process. In order to get the area, we want to take the antiderivative from where x is equal to -2 all the way up to where x is equal to +2 of this x cubed dx. And so when we plug this in, just like last time, we know, again, I'm sort of looking at this part here. When I take the antiderivative of that, I know I'm going to get x to the 4 over 4. And so when I do that, if I'm looking for x to the 4 over 4, it would be from this point of -2 all the way up to 2. Oh, see, hardest part is, let's color code that. -2 all the way up to 2. And just so that you can get a clear sense of like where I'm getting everything from, and it's crystal clear to you, hopefully. And that doesn't really look like an exponent. Let's fix that. So if that's what we're doing, maybe I can just keep it going to the right here so that it's nice and easy for us to see it. So what we end up getting, I'm going to slide that over a bit. Hopefully this is all working out and you can see. So we would want to start again with the upper limit. So we're going to start by plugging in this 2 here. So I'll do this part in the green. So we'd have 2 to the 4 over 4 when we plug that in there. And then for the other one, we would want to subtract from it the lower limit, which is this -2. So I'm going to do the same thing, -2 to the 4 over 4 as I go through this. And then this time I am going to run out of room, so I'm going to go down below. But when we work our way through this, I would actually get, notice the negative doesn't really matter because our exponent is positive or even. Even is what I meant. But basically, do you see that we're going to get the same number? We're going to get 16 over 4 minus 16 over 4. So when we work our way through everything, it works out to 0. And it actually kind of makes sense because if we go back to the diagram over here, you can tell, okay, it's supposed to be perfectly symmetrical. I didn't draw it perfectly symmetrical, but it makes sense if we're taking the area under the curve from the negative portion and the positive portion there, that it all balances out and it's giving us a value of 0. So basically because, to make sense of it, maybe I'll do it in the purple so you can see, because there's the lower limit, or it's in the negative area there. So you can see the reason that it ends up canceling out and giving us a value of 0, or hopefully you can, and it's looking like it's making sense. Okay, so then here's the next one. Let's take a look at the area between sine x and the x-axis from x equals pi over 6 to x equals pi over 2. Again, you didn't necessarily have to, but I think it would be helpful to build in a little bit of a review. So if we think back to what a Sine X graph looks like, it does go, I'm only going to draw like half of a period. Like it would keep going, but whatever. We only care about that part because notice how this would be up to this point where it's equal to pi. And then to put things into perspective, remember that halfway here would be pi over 2. And I'm just going to roughly fit it in here. Like we could distribute this or chop it up evenly, but we're going to say around here would be pi over 6. Just a quick like fraction recap, because I noticed grade 12s don't struggle so much with trig. It's more that they're having troubles with their fractions. If the 6 or the denominator is larger than the pi over 2, that actually means we have a smaller number, right? So it makes sense that pi over 6 is to the left of pi over 2. Again, just to start thinking again in terms of fractions and how to make sense of all this stuff. So I hope that that is kind of making sense here. And if we are looking for the area or the distance between these values here, let's take a look at how that shows up. So if we have pi over 6 there, and then, I don't know, is my color coding not really working here? If we have pi over 2 here, then the area underneath, or the part that we're interested in, is this part here, which I'm just going to scribble in. I have to say there's something so fun and rewarding about coloring on this thing. Okay, so that's the part that we're interested in, although I kind of have missed the lines and didn't do the best job, but I tried. So that's the part that we're looking at or that we're interested in, and we are still doing the same type of thing as before. So if our function that we're looking at is sine x and the x-axis, well, if we want to think antiderivative, so if we want the antiderivative of sine x dx, we would get, again, we're interested in that part, the antiderivative of it, we know, would be negative cos x. Based on our knowledge of what derivatives are, we're just working backwards and looking at it backwards. So what that means is I want negative cos x from pi over 6 up to the other part here, which was pi over 2. So notice, I want you to pay attention to the similarities and the pattern. Each of the questions we've done so far, they've been slightly different, but we're following the same steps and the same pattern. So you take the antiderivative, you find the lower limit and the upper limit, and you work your way through it that way. So working our way through it that way, I'm going to go down below here so that we can sort of see and keep track of what's happening. Basically, I would want to start with my negative cos pi over 2. So remember, we always start with the upper limit first. So negative cos of pi over 2. And so, yeah, we do need our past trig knowledge in order to be able to work with this stuff. Minus, and now I'm going to subtract from it the lower limit, which is negative cos pi over 6. Another common mistake I see is that a lot of people leave off the negative sign, so make sure that you are writing out each step, because you'd be shocked. Lots of people just forget to do that, and it does impact everything that you do afterwards, so pay attention to that. And then we can think our way through, because we kind of know, again, what our cos graph would look like. Negative cos of pi over 2 is the point where our cosine graph would be going through 0. So actually, sorry, color coding. I'd get a 0 from there. And then notice how it's minus minus. So I know that this is actually going to end up giving me a positive. And again, cosine of pi over 6. Again, I hope you're recognizing or remembering pi over 6 is one of the ones from our special triangles that we reviewed last day. So remember, if we were to chop our triangle in half, 1, 2, and root 3, and then remember that we would have the pi over 6 would be this one up here, and pi over 3 would be this one down here, because the one at the top is the one that we've chopped in half, so you know that's always a smaller angle. So just to throw in some review and to remind you of this. I've made a big mess of this, but hopefully you're able to make sense of it and follow along. So if we're looking for the cosine of pi over 6, it'd be adjacent, so this over hypotenuse. So we would get root 3 over 2. The other one was just 0, so after all that work, our answer is just root 3 over 2. And you can see the steps in the process to get there. So hopefully the step-by-step process and manner that we use to go through it will help bring you some clarity and make it a bit easier to work with. Don't let the different functions throw you off. The last ones we just did basic like cubic and quadratic functions, and then this time it was trig. So it doesn't matter what the original function is. Keep in mind that you're using that same pattern of finding the antiderivative, looking for the upper limit, subtracting the lower limit, and that gives you the area in between them. So your work is this stuff, page 454, 1 to 4 odd letters, number 5 and number 6, all of them, and I hope you found that helpful.